Right now, as you watch this, mile-long trains are hauling the raw materials and finished goods that your entire life depends on: coal, grain, cars, and the containers full of everything you'll ever buy. Freight rail moves billions of tons a year, and almost none of it happens where you can see it. This is the hidden backbone of the economy, and here's how it actually works. Start with the scale. Freight is the circulatory system of the global economy, and its demand is projected to roughly triple by 2050. Moving all that weight has a cost. Freight transport is responsible for around 8% of the world's greenhouse gas emissions, and closer to 11% once you count the ports and warehouses, which is exactly why how we move it matters so much. Here's what makes rail special. Unlike public highways, freight railroads are largely privately built, maintained, and paid for. And the return is enormous. Every dollar invested in rail generates an estimated $2.50 in wider economic activity, and each railroad job supports nearly 4 more across the economy. That efficiency comes from 2 places: the nodes where cargo is sorted and the mechanics of the long-distance haul. Let's start with the sorting. A freight train doesn't usually go straight from door to door. It arrives as a jumble of cars bound for a dozen different places, and it has to be taken apart and rebuilt. That job happens at a classification yard, also called a marshalling yard, where incoming trains are disassembled and their cars regrouped by destination. Railroaders call it blocking, and it's the beating heart of the network. There are 3 ways to do it. A flat yard sits on level ground, so a locomotive has to physically shove every car into place, slow and labor-intensive. A gravity yard uses a permanent downhill slope, but it's at the mercy of the weather, which changes how freely the cars roll, so it's mostly obsolete. The modern answer combines the best of both: the hump yard. A hump yard is built around a single clever idea: a small artificial hill. The whole facility is a linear assembly line. A receiving yard where trains arrive, the hump itself, a wide classification bowl where the sorting happens, and a departure yard where new trains leave. A locomotive slowly pushes the arriving train up and over the crest, and from there, gravity takes over. The process is beautifully simple. In the receiving yard, crews inspect the cars and bleed off the brakes so the wheels roll free. A switch engine pushes the train toward the crest, and just as each car reaches the top, a worker pulls a single pin to uncouple it. The car rolls down the far side on its own, and a cascade of automated switches steers it onto exactly the right track in the bowl below. But a car rolling downhill on its own is a problem. Let it run free, and it slams into the cars already parked below. So the yard controls its speed with retarders, powerful, computer-controlled brakes built into the rails that squeeze the sides of the wheels as the car passes. The energy is pure physics, the height of the hump versus the friction and braking that bleed it off. The computer weighs each car and reads the wind and temperature, releasing it to couple at a gentle 2 to 4 miles per hour. The number that rules a yard is dwell time, how long a car sits from the moment it arrives to the moment it leaves. It can be most of a day, and it's fragile. If too many trains try to depart at once, the whole yard clogs. The leverage is huge. Trimming average dwell time by just 15% lifts the speed of the entire network by around 2 miles per hour. In a system this big, that's a staggering gain. The second great node is intermodal, and it rests on one of the most important inventions of the 20th century, the shipping container. A standardized steel box can travel from a factory onto a truck, onto a train, onto an ocean ship, and back again, without the goods inside ever being touched. The freight moves, the cargo never gets handled. It works because the box is standardized, 20 and 40-foot international containers, plus 53-foot domestic ones. That single dimension is what lets a crane in Shanghai and a train in Kansas handle the same unit. The short hops at each end, from the port or terminal to the customer's door, usually within 15 to 50 miles, are handled by trucks in a step called drayage. Rail does the long middle, trucks do the first and last mile. Inside the terminal, 2 machines do the heavy lifting. Gantry cranes span several tracks and truck lanes at once, running on rails or rubber tires and stacking containers 5 or 6 high, dense and efficient, often drawing power straight from the grid. Reach stackers are the nimble alternative. Tire-mounted trucks with a telescoping arm that can pick up 45 tons and dart between stacks. Cheaper, but hungrier for space. There are 2 ways to put freight on a railcar. Container-on-flat car strips the box off its wheels and drops it into a special well car, low to the ground, aerodynamic, and stackable too high. Trailer-on-flat car loads the entire highway trailer, wheels and all, riding up top, simpler to load, but taller, draggier, and heavier. For the long haul, the low, stackable container wins almost every time. And that's the trick that reshaped North American freight: double stacking. By dropping containers into well cars and stacking a second one on top, a railroad doubles the cargo it can carry in the exact same length of train. Same crew, same locomotives, same track, twice the payload. It's one of the quiet reasons rail can undercut trucking on long routes. Not all freight trains are built the same way. Railroads run 3 basic types, each a different bargain between cost, speed, and volume. Unit trains, manifest trains, and intermodal trains. Each one moves through the network in a completely different way. A unit train is the specialist. It carries a single bulk commodity, coal, grain, ore, or crude oil, from one loading point to one destination, in 100 to 120 identical cars. Because every car is going to the same place, it skips the classification yards entirely and just shuttles back and forth. Some are even unloaded on the move, rotary dumpers flipping each car upside down without ever uncoupling it. A manifest train is the opposite, a mixed bag of boxcars, tank cars, and auto racks for dozens of different customers. Because every car has its own destination, the train must be sorted and resorted at yard after yard along the way. It's the flexible option for smaller shippers, but it's slow. A single boxcar can spend more than half its entire journey sitting still in yards, waiting its turn to be sorted. Then there's the problem of sheer size. To drag a train that can average nearly 4,000 tons over a mountain pass, you can't just add more locomotives to the front. The couplers would tear apart. So railroads use distributed power, locomotives placed in the middle and at the rear, controlled remotely by radio from the lead cab. Spreading the pull eases the strain on the couplers and breaks the train more evenly, which is how trains keep getting longer and heavier. So why go to all this trouble instead of just using trucks? Physics. A rubber tire squashes against asphalt and fights the road the whole way. A hard steel wheel on a polished steel rail barely deforms at all. Its rolling resistance is roughly 5 times lower. That single mechanical advantage is why a freight train can move a ton of cargo 3 to 4 times further on a gallon of fuel than a truck, up to 500 miles per gallon per ton. That efficiency shows up directly in carbon. Measured per ton-kilometer, road freight emits 50 to 150 grams of CO2. Rail emits just 20 to 50, up to 75% less than trucking. Only ocean ships do better, thanks to their sheer size. And there's a hidden ledger too. Trucking's uncounted external costs, road wear, accidents, dirty air, run 6 to 8 times higher than rails. The efficiency is real, and most of it is invisible. And it's still getting cleaner. In Europe, more than 80% of the freight rail network already runs on electricity. In the yards, multi-engine genset switchers cut fuel use by up to 40%, and particulate filters strip out most of the soot. On one European corridor, shifting around 240 truckloads a week from road to rail cuts roughly 11,500 tons of CO2 every single year from one route. So the next time a freight train rumbles past a crossing, remember what it took to build it. A train torn apart and rebuilt in a hump yard. Containers stacked too high and handed off between ship, rail, and road. And the simple physics of steel on steel doing the work of hundreds of trucks. It's the hidden backbone of the modern world. If you found this useful, subscribe to Rams Ready for more deep dives into the engineering behind the railways, and I'll see you in the next one.